Welcome back, everyone, to these celebration activities for the 60th anniversary of the Mathematics Department of Cinvestav. Our speaker today is a world-class leader in computational geometry and topology. He is professor at the Institute of Science and Technology in Austria. He has written over 200 research papers and 4 books, and his research has received over 3,000 citations. He's a co-founder director of GeoMagic, currently a 3D printing company. He's a member of the Austrian and German Academy of Sciences, and he has received international awards recognizing his contributions, most recently the Wittgenstein Prize, one of the highest Austrian recognitions supporting excellent scientists who have produced exceptional scientific work and who occupy a prominent place in the international scientific community. It is thus my great pleasure to deeply thank Professor Herbert Edelsbrunner for kindly accepting to deliver this talk as part of the celebration activities for our 60th anniversary. So, without further ado, I warmly welcome Professor Edelsbrunner to deliver this talk on distortion on the average and in expectation.
Thank you very much for giving me this opportunity. I feel honored to be able to address you at this occasion, at the 60th anniversary of mathematics in Cinvestav. I should also say that it is a little boring to talk to the computer for 50 minutes without any feedback. So if you feel like asking a question during the talk, feel free to do so. In particular, if it's a short question, I try to give a short answer so it doesn't interrupt the flow of the talk, but it makes it more lively. So I would very much welcome such interruptions. Let me try to share the screen now. So this is my talk. This is joint work with Anton Nikitenko. I met him maybe about 10 years ago in Russia, and then he became a student at ISD, and then he spent 2 years as a postdoc with me, and we worked together on this distortion on the average and an expectation. And this is really a geometric question or a geometric topic, but there are strong probabilistic aspects to it. And to give you a feeling of what I want to talk about is it's about measuring shapes that are difficult to measure. And this is just a random picture of a tree that I got off the internet. The point I would like to make is the total surface of the leaves of this tree would be interesting to know, but I don't think we know it. I've never seen any statistics about areas of leaves of a tree as they change during the seasons, or maybe even during the day when the sun shines or doesn't shine. And I guess the difficulty is that there are so many leaves, and even the area of a leaf itself is not so easy to define exactly. It looks mostly like a two-dimensional object, but somewhat fractal, somewhat three-dimensional. In any case, there are many such instances where it might be useful to measure things, in particular the area of leaves, maybe even a curvature. But it seems a little bit out of the question because we don't have the tools for that. And I got reminded of an event thousands of years ago when Archimedes figured out how to measure complicated shapes such as gold crowns. Namely, he put the crown into the water and measured how much the water level rises, and that's the volume of the crown. And the relevance of this invention was that it was easy to weigh gold crowns, but it was difficult to measure the volume of it. And the weight and the volume for a particular material are in a particular ratio. So people, for example, replaced parts of the gold crown by silver, such that the weight is the same, and nobody figured it out until Archimedes came along and was able to measure the volume. Now, I don't think such a breakthrough of such magnitude is possible nowadays, but I hope to contribute to methods that make things measurable that are at the moment difficult or impossible to measure. And I think probabilistic methods are a prime ingredient in this undertaking. Okay, so that's the motivation. And next I would like to tell you about a particular approach to this and what it means geometrically and probabilistically. I start with the intuition. Suppose I have a disk, and we know the area of the disk. It's a unit disk, so the radius is 1, therefore the area is r squared pi, so that's pi. And one way to measure it is I put it on a square grid, like a square paper, and then I count the number of vertices of the square grid inside of the disk. And as you can see, this approximates the area of the disk. And because each such vertex is surrounded by a unit or by a square of a certain side length. And then if I let the grid shrink, meaning gets finer and finer until there is infinitely many points, then the area of how I measure it in the grid goes towards the area of the disk. So I say that the distortion goes to 1 as the grid gets finer. This, by the way, is a problem that also goes back way 2 centuries or something to Gauss. Gauss asked first this question. Namely, he was interested in how big can the difference between the number of points inside a disk and the area of the disk become. And this error function is still not pinned down exactly. There's a lot of work on it and very good results, but we don't exactly know what the error can be. But in any case, the error goes to 0, so the distortion in this case is 1. I'm more interested in the length of the circle. So suppose I do the same thing for the circle. Again, I put it in a square grid, and then I reconstruct the boundary by connecting centers of squares. Namely, I connect 2 centers if the circle intersects the edge between the 2 squares. So I have the edges that are intersected by the circle in pink, and then I take the blue dual edges of those pink edges. And this gives me a staircase that goes up from left to the top, then it goes down from top to the right, and then goes down from right to the bottom, and then up again from bottom to the left. So we can ask ourselves of how long is this an approximation of the perimeter? Again, unit radius. So the stairs from the left to the top have length 2, because you go to the left along the radius and up along the radius. So in total, you get length 8, or approximately 8, because as the square grid gets finer, get closer and closer to the circle, then it approaches 8. But we know that the circle has circumference 2 pi. So the distortion is 8 divided by 2 pi, or 4 divided by pi. And that's 127 and something. So this magical number comes up. We don't get 1 anymore, but we get a number that is repeatable. And in some sense, well, I want to show that this 1.27 is universal for other objects also. For example, how about we look at a line? If I do the same experiment with a straight line, I get a staircase that just increases from left to right. And I always go left, left, up, left, not strictly alternating, but somewhat alternating. The distortion in this case is an interval. It could be 1, namely if the line is completely horizontal or vertical. But if it's diagonal, then I alternate between left and right. Sorry, with left and up steps. And the distortion becomes square root of 2 because the line proceeds along the diagonal, which is only square root of 2, while left and up steps have length 2. All right, so the difference between the line and the circle will become interesting because the circle somehow represents every direction uniformly, whereas the line represents only one direction. And the square grid is biased. It's biased towards or against some directions. It measures things differently along the diagonal from horizontal lines, for example. We'll come back to this point a little bit later. Let me venture to 3 dimensions. How about a plane in a cubical grid? So this picture here is a perfectly diagonal plane, which means it's normal. Its normal vector is the vector 1, 1, 1. Then I get the surface of this stacked cubes. And a little calculation tells us that in this case, the distortion is square root of 3. So it's more than in 2 dimensions. Just a projection of these sides of a unit cube. But if I do this for the sphere, I get again a particular distortion. And we can see this as follows. Suppose the approximation with little cubes, the cubes get smaller, so the approximation gets better and better. What is the surface area of the union of cubes? There are 6 major directions to look at this construction, namely from the front and the back, left and right, up and down. And then from each of those directions, we see approximately a disk. So these faces add up to the area of a disk, which is pi. Since we have 6 such directions, we see the total area is 6 pi, all right, in the limit. But the real area of a sphere, as you will remember, is 4 pi. So the distortion is 6 pi over 4 pi, which is 3.5. Sorry, 3 halves, which is 1.5. And I want to say that this is also a universal number that is useful. Okay, with this introduction, let me get to the results. First, the definitions, and then I tell you what we can prove. So I already said that one of the disadvantages of the square grid or the cubical grid is a bias towards certain directions. And I would like to have a grid which is not biased in any direction. If it's a regular grid, it doesn't exist. But if I take a uniform distribution of points, a random set of points, and then construct the Voronoi diagram, then there's no directional bias at all. So this uniform distribution, I call it the Poisson point process. This is a small window of a Poisson point process. You see the points. And this is the Voronoi tessellation. So the definition of Voronoi tessellation is for each point, I delineate the region of points where this point in the center is the closest in Euclidean distance. So these are convex polyhedra. In a plane, they're convex polygons. And they nicely tile space. They don't overlap. except that they touch along edges and sometimes at vertices. The dual of this construction is called the Voronoi mosaic. And to get that is for every Voronoi edge, this is a black straight edge, I draw the blue edge normal to it, connecting the centers of the Voronoi regions. And if the points are in general position, which happens with probability 1 in the Poisson point process, I get a triangulation. So often the Delaunay mosaic is called the Delaunay triangulation. So you see the triangles here. And I want to mention that there's a one-to-one correspondence between the Voronoi tessellation and Delaunay mosaic. That is, for each edge of the Voronoi tessellation, there's a dual edge of the Delaunay mosaic. For each vertex of the Voronoi tessellation, there's a dual triangle in the Delaunay mosaic. And for each Voronoi region, there's a dual Delaunay vertex. Okay, so that's the reason why this is called dual, because this bijection that I just outlined is inverts dimensions, but preserves incidences. And the notation that I use for that is for a cell of the Delaunay mosaic, I already write gamma, and a dual cell in the Voronoi tessellation, I write gamma star. And note that the dimensions of gamma and gamma star are complementary. So if I'm in D dimensions and gamma is P dimensional, then gamma star is D minus P dimensional. And the most important definition is then, if I'm given an object such as this red straight line, then I define the Voronoi path as the set of Delaunay edges that are dual to Voronoi edges intersecting the line. So here you see the line intersects this sequence of regions. For each Voronoi edge crossed by this line, I draw the blue Delaunay edge. And my short form for this is SCP, because in the plane, traditionally, it's called a Voronoi path, but in higher dimensions, we want to call it a Voronoi scape, like landscape, but shortened to scape. Mostly though, I will talk about one-dimensional objects today, but the results are all higher dimensional also. A little bit about prior results, prior work. So I found 2 papers on the subject. The second one indeed motivated us to think about the problem in the first case. They're both about a Voronoi tessellation for a Poisson point process. So I call A Poisson point process. And they only consider the Voronoi path of a line. So in 2000, Pacelli, Chumachenko, and Tsuyev proved that in the plane, the expected distortion is 4 over pi. That's what I told you about the circle. In 2018, so 18 years later, De Castro and De Villiers, they extended this result to D dimensions, but they didn't have the precise distortion factor. They just proved that it's square root of 2D over pi plus some error term. And what I want to speak today is an improvement of this second result and the vast generalization, namely to all dimensions D and all dimensions P, where P measures the dimension of the shape that we take the Voronoi scape of. And here is a table of the constants we find. Let's see, so far we talked about a 2-dimensional case. So this is the second column. The one in the diagonal just means that in 2 dimensions, to measure area, we get a distortion of 1. To measure length, we get a distortion of 4 over pi. And I'll be precise later in what sense we get this distortion 4 over pi. In 3 dimensions, volume we can do with distortion 1. Area we can measure with distortion 1.5 and length also with 1.5. And this 1.5 I would like to compare with the result of the second paper, where it was 6 over pi square root of, and this is 1.38. So the second result is not really close to the reality of 1.5. It's kind of off a little. In any case, we have exactly the bound. I think I circled the wrong 3.5. It should really be for p equal to 1, because you talk about one-dimensional shapes. But for 1- and 2-dimensional shapes, the constant is the same. So this is the table. Note that you see the Pascal triangle in the table. Namely, if you take the even rows and the even columns, you get the Pascal triangle. Indeed, the general way of writing the distortion constant is this way, as a binomial coefficient of half integers. And using gamma functions, it can be defined exactly like this, or double factorials, it's this expression. And we call this distortion factor d sub p comma d. So again, what is to the indices mean? D is the dimension of the ambient space. P is the dimension of the shape I'm measuring. All right. So here are there's two results, or I state the result as two theorems. The first one is about average distortion. And this is true for any Voronoi tessellation that has the mixed regularity property. I'll talk about this later. So this is a mild property that the tiling of space has to fulfill. In this case, if I have omega, which is a p-dimensional rectifiable space or object, then the average p-dimensional volume of a Voronoi scape, and by average, I mean, I look at the placements of omega in all placements possible inside of a big ball of radius r, big R. Then this average p volume is the original p volume times the distortion factor. Then there's an error term, little o of 1. And this is true when r goes to infinity, meaning the ball where I take the average over is getting larger and larger. Okay, and let me tell you the second theorem, and then we maybe compare them. The second theorem is about the Poisson point process, PPP. So here A is a Poisson point process. I take the Voronoi tessellation. The process is with a positive density, so there are points everywhere. Then the expected distortion of omega, the expected p-dimensional volume of my Voronoi scape is the distortion factor times the original distortion, the original p-dimensional volume. So the distortion, the expected distortion is exactly this d sub p comma d. That's the result. So the difference between the two results is that for a Poisson point process, I can only do one experiment. Like I put omega in there, I construct the Voronoi scape, I measure it, and then the expected p-dimensional volume is distorted with this d sub p comma d. So this gives me a good estimate. If I don't have a Poisson point process, but rather maybe a cubical grid or something, then I have to average over all poses of the object. But this says that this result, this distortion constant, is not a probabilistic property, but it's rather a property of the space. Because the first theorem deals with no probability. It's just the average over all placements. And the second theorem comes about because the Poisson point process is unbiased, and so I can do it in one experiment. All right, so that's the theorem. I'll say a little bit about the methods and the proof. So of course we need the Gramanian. So for people who are not familiar with this, short introduction. The Gramanian is the the collection of all p-dimensional planes in d dimensions that pass through the origin. For example, the lines in the plane all passing through the origin. So you get a pencil of lines or pencil of p-planes in d dimensions. And a little exercise shows that the dimension of this Gramanian is p times d minus p. So this is really a manifold of this dimension. And this manifold, and we call it a manifold because every point of this manifold corresponds to a p-dimensional plane. So it's a convenient language to talk with it, to talk about it. Here is one exercise. Let E be a unit cube, p-dimensional. Okay, sits in space. Let me take a p-dimensional plane L. So this is p-dimensional. And now let me project the p-dimensional cube onto the p-dimensional plane and write this for the p-dimensional volume. And I'm interested in the average of this p-dimensional volume, for example. And in 2 dimensions, this is a slightly interesting geometric exercise. So in 2 dimensions, I would have a 1-dimensional, so P is 1, D is 2, a 1-dimensional unit cube. So here is the unit length line segment. I pick a random line, L. I project E onto the line, and I take the length. And I'm interested in the average. And you get this average by turning this line through 90 degrees. The length of the projection is therefore the cosine. So you get the integral of the cosine for angles between 0 and pi over 2. This integral is 1. The range is length pi over 2. So the average is 1 over pi over 2 or 2 over pi. So this is the average length of the projection. And we denote this by m sub p comma d super 1. So this is the average. Here I have a superscript 2, which means I take the square of the length of the projection. And this has a beautiful geometric interpretation, because if you turn this line through 90 degrees, you get the red segment on the one side and the blue dotted segment on the other side. And in total, the red segments have the same length as the blue segments. It's completely symmetric. Also, the square of the red segment plus the square of the blue dotted segment is 1 by Pythagoras, because they're the right angle. Which means that the average square of the red segment must be 1/2, because the 1 needs to be shared in equal portions by the blue dotted and the red. And it turns out that these two numbers, m, the average, and m super 2, the squared average, they make up the distortion constant. I'll be a little bit more precise. So the chaff projection moment is, I take the projection, I take the p-dimensional volume of it, and I take the chaff power. And I integrate over all p-planes, and I call this the chaff projection moment. And then the lemma says, for j equal to 1, we have this equation. So this constant here shows up in Crofton's formula, which is a classic topic in geometry. So I'm not going to get into details of how to compute this constant, but I can tell you the details about how to compute the second moment. But before I do that, the ratio, so the first moment divided by the second moment, that's the distortion constant. Okay, so a short proof that the second distortion moment is 1 over the binomial coefficient. There's a beautiful theorem which, due to Cauchy-Binet, which extends the Pythagorean theorem. It says that if you have a unit cube of dimension p, and then the square p-dimensional volume, is the sum over all projections on p-dimensional coordinate planes of the square of the p-dimensional volume of the projection. Okay, so here's the formula. Because I take a unit cube, this is 1. And so I take a sum over a binomial coefficient many terms. And the expectation of that, if I go over all p-dimensional planes, is the same for every coordinate plane. So it must be 1 over the binomial coefficient. All right. So much about projection moments. I get a little closer to the proof of the two theorems. Namely, the notion of tiles is important. The tiles somehow divide our space into regions where the distortion is predictable. Here's the construction. I'm going to take a Delaunay cell gamma, and I consider the dual Voronoi cell gamma star. And I'm interested in lines that intersect gamma star such that the projection of gamma onto the line is a point X. So I'm interested in pairs X and L. And this should remind you of the construction of a Voronoi scape, because I'm intersecting the Voronoi cells and I take the dual Delaunay cells and project them. So a p-tile of gamma and gamma star is exactly the set of pairs X and L, where X is a point and L is a p-plane, such that the p-plane intersects the Voronoi cell and a point is in the projection of the Delaunay cell. What you notice maybe if I turn the line L, but intersect the Voronoi cell in the same point and talk about the same point on gamma on its projection, then the point X describes a circle. Again, Pythagoras, namely the smallest circle that goes through the point chosen on gamma and the point chosen on gamma star. So if I look at the p-tile itself, it's really a union of circles, at least in the projection into the t-dimensional plane. So here is this drawing, a union of circles. For every pair of points, one in gamma star, I get a circle. So I get this kind of a torus-like objects. But note that these objects live in d plus p times d minus p dimensions. So the second part is the space where the p-planes live, and d is the Euclidean space where our problem is. But we observe that the projection to d dimensions is small, because usually the Delaunay cells and the Voronoi cells, they are close by. So these things, they're called tiles, they are not very big, and that will be important. In particular, they're not very big in terms of diameter, extent in space, but we can actually compute its volume exactly. So the volume is the volume of the Voronoi cell times the Delaunay cell times the Voronoi cell divided by the binomial coefficient. Here's a little proof. Let's see, the volume of this tile is, I integrate over all p-planes. On each p-plane, I integrate over all points y that are in the projection of the Delaunay cell. And then I integrate over all points z in the normal space, so that I talk about the line L plus z, because L is only the lines that go to the origin, but I need general lines that intersect the Voronoi cell. And then I integrate this. The second part is the size of the Voronoi cell times the cosine of the angle between L and gamma. Oh, Ln gamma star. No, Ln gamma. The first part is the size of the Delaunay cell, and again times cosine of the angle between L and gamma. So I get the cosine square here. Here I just get the product of the sizes of the two cells. The integral of the cosine square, this is like the Cauchy-Binet theorem, the generalization of the Pythagoras theorem, which tells us that the average size of a projection onto a coordinate plane, p-dimensional coordinate plane, is 1 over the binomial coefficient. So this is the 1 of the binomial coefficient. So this gives the theorem here. All right. So now I get to this property that I introduced when I stated the theorems, this mixed regularity. So I say that a point set A has mixed regularity if the boundary tiles of a ball of size of radius r have measure less than the dth power of the radius. What does this mean? The tiles we already know. I'm talking about a big ball, and then I grow it to take the limit. But then some of the tiles, the projections of the tiles lie inside of the ball, and some of them lie outside, and some of them are partially inside and partially outside. The boundary tiles are exactly the ones that are partially inside and partially outside. And so these are the ones that cause trouble, because when a tile lies completely inside, I can just integrate over the tile and know exactly the distortion constant, which is the one that I gave you. If a tile is partially inside and partially outside, it contributes some inside and others not, and it's unpredictable. But since the tiles are small, the total measure of the boundary tiles is usually of a lower order than the tiles that are inside, just because the boundary measure of the ball is less than the d-dimensional measure of the ball. And so for such sets A with that have the mixed regularity property, the theorems that I was talking about hold. And just to give you a feeling for it, when you have a Delaunay set, I remind you a Delaunay set is when there's an upper bound on the size of a ball that can be empty of any points. And there's a lower bound on the size of a ball that contains 2 points. So a Delaunay set has always the mixed regularity property, because there cannot be large empty spaces of points. And also, if you take a Poisson point process in Euclidean space, then it has the mixed regularity property in expectation. And otherwise, all natural point sets have the mixed regularity property. An unnatural point set that does not have this property is if the gaps between the points, as you get closer to infinity, get larger and larger, like exponentially growing. So they have a dense point set, and then you have a less point, and the density decreases exponentially. That would be a counter example to mixed regularity, and then our theorem breaks down. Okay, so as a step towards proving it, there's a geometric puzzle that I prepared. There's something called a mixed complex. And so I would like to introduce that first and then ask a question about it. So here is the Voronoi tessellation overlaid with a Delaunay mosaic, same as before. But now let me do the exercise of taking every Voronoi cell and shrinking it by a factor of 2. Towards the center, towards the point that generates the Voronoi cell. Okay, then I have space in between, and then I can shrink now the Delaunay cells also by a factor of 2 and fit them in between. And the Delaunay triangles in this case, they shrink towards the dual Voronoi vertex, and they fit perfectly in sharing vertices. Okay, so in the plane, then you're left with the Voronoi cells and the Delaunay cells, both smaller, plus the rectangles. And now the question would be, how big is the rectangle area? And the answer in the plane is easy, because the area covered by the Voronoi cells is 1/4, because I shrank by a factor of 2. The area, total area of the Delaunay triangles is also 1/4, because again, I shrank by a factor of 2. So 1 minus 2/4 is 1/2. So the rectangles cover half the plane. And this should be understood again with this growing ball and taking the limit and stuff. But now let's do the same thing in 3 dimensions. In 3 dimensions, there's one more case. We have the Voronoi cells, the Voronoi planes times the Delaunay edges, the Voronoi edges times the Delaunay triangles, and then the Delaunay tetrahedra. And now it's not so clear anymore of how much space for example, the Voronoi planes polygons times the Delaunay edges occupy of 3-dimensional space. It turns out that with what I told you so far, I can give you an answer. Namely, what I'm talking about is the sum of the areas of the mixed volume. So take a Delaunay simplex times a Voronoi cell, and it's exactly the binomial coefficient times the space. So if I divide this by 2, then I get this mixed volume construction, and this tells me how much of space is covered. So I found this, the proof is convincing, I think, but I found the result interesting because intuitively, I would not expect that if I mix the volumes of the Delaunay cells times the dual Voronoi cells, that there's some reasonable number coming out. But it turns out that there is. Okay. This is pretty much already the proof of the 2 theorems that I showed you. So I want to skip the rest and go to some experiments. So we ran these experiments, and then Ranita Biswas and Tanya Ezubova did that. And I can tell you a little bit about how we measure simple objects, but we could also measure complicated objects. So here's a simple object, a circle in the plane. You see a Voronoi tessellation of a Poisson point process in a plane. You see the Voronoi path. And we did experiments. So for each density, we took 100 trials. So the number of points is not an integer, because in a Poisson point process, you only given a density, and then the number of points itself is a random variable. But we roughly go from 100 to 800 to 6,000 to 50,000. That's the number of points. The average distortion. And remember, the distortion in a plane we expect is 1.27. So it converges to 1.27 fast. So for a relatively fine Voronoi tessellation, it's already 1.27. Here you see the variance also goes down to 0. This column, maybe I should explain. Namely, when you have a shape which is not straight but turns, it's possible that the circle, like the circle, it's possible that the circle intersects a Voronoi edge twice. In which case I get, in the Voronoi path, I get an edge out and coming back again, and then I continue. We call this a leaf here. Which means that in the reconstruction, the Voronoi path of the circle is not necessarily homeomorphic to a circle, but it's necessarily homotopy equivalent to a circle. All right, but we see actually that the number of such occurrences also goes to 0. More generally, it's not only that you could get an edge going out of the circle, actually there could be a tree growing out. In graph theory, these objects have a name. I think they're called cactus. So a cactus is a tree with a single circle, a single cycle. So for the circle, we really get a cactus. The number of leaves, though, goes down, so we almost never see them. All right, here's another experiment with a clover in the plane. In the middle, there's a little bit of a mess. And I'm not sure I want to highlight this. I guess I could go in there, but not enough to really see some interesting stuff. But we do see that the number of leaves increases. So because the reason is really because the clover is topologically more complicated. It's not a one manifold anymore because there's a crossing, and this crossing has degree 8, plus 2 of the edges that go out in the same direction and only curve away, and pairs of the 8. So this causes topological trouble, but it's still homotopy equivalent, and the results are very nice. Again, we get 1.27 for the distortion, with the variance going to 0. We did the same thing in 3 dimensions. So here you see a trefoil knot. The Voronoi tessellation we didn't draw, but we draw the points. And we have roughly the same number of points. And remember, in 3 dimensions, the distortion factor for p equal to 1 goes to 1.5. And at the beginning, it fluctuates a little bit, but then very soon it's very close to it. The variance, again, seems to go to 0. The number of leaves also seems to go to 0. For the plane, the number of leaves, I can give a back of the envelope argument that it has to go to 0. In 3 dimensions, this is not so easy anymore. So I don't think I have a proof that this actually needs to go to 0. At the time of this talk, we didn't have much on higher dimensional things, but we do have some results on 2-dimensional, like the introduction with the leaves on a tree. But maybe I used the time of my talk pretty much and should give you time to ask questions. So thank you for your attention.
Thank you very much. May I ask everyone to please unmute yourself to express our appreciation to the speaker?
Thank you very much.
All right. I think we're ready for a short session of questions or comments. So if people have anything, some questions or comments, please go ahead. I think I have a couple of questions and comments. One is really very general. I wonder if these kind of ideas could be used in image recognition. That would be one question. Image recognition.
Yeah, it's interesting. So my thoughts were always going in the direction of images, like medical images, and measuring like length of arteries or total curvature of organs and so on. But you're asking for recognition. So can I recognize whether I see a heart or a lung or something with these methods? I guess in the sense that if I can measure area or curvature reliably, this gives me, of course, a lot of information also of what kind of object I'm looking at. So I'm still like to be focused on the measuring part of it, but the recognition is not independent of measuring. That's a good idea. Could try that.
Okay, and I have another general question. I just was wondering, when you were talking about tiles, the volume of tiles, this was in section 3.3, more or less.
Yeah.
You define the tiles. And it remind me a little bit of the universal vector bundle over Gramanians. So I wonder if this is some sort of a fiber space and with some sort of a universal property.
I would guess yes. I'm not so familiar with fibered spaces and the theory behind that. But those tiles, they certainly, they partition the space or they decompose it rather, because again, they share boundary, this high dimensional space. And also they have this nice property that within a tile, if I take the average, I get exactly the distortion factor. So I have complete control over where the distortion happens. Now, if maybe one trouble with this partition is that as my Voronoi tessellation gets finer, the tiling also gets finer. So I don't get long fibers, but I get very short cycles that decompose my space. And I don't know how this fits in the theory of fibered spaces. Maybe you know more about it.
Thank you. Thank you. Any other question or comment?
So it's probably the case that you may express this using vector bundles equipped by a connection or something like that.
Yeah, I think it's probably the case. Yeah, I could do that, but it's also not. It's not really necessary. I mean, for the proof, I just need this decomposition, and then it's fairly elementary. I don't need high-browed methods for mathematics in order to finish the proof. But it might be interesting to go deeper into the properties of those decompositions with tiles. I agree with that.
Well, I think this is a good moment to stop the recording.